Hello and welcome back to the channel and to this, the second episode in this series concerning the NTSB accident report concerning the US Airways flight 1549, loss of thrust in both engines and encountering a flock of birds and subsequent ditching in the Hudson River. This is video 2, so what we're going to talk about today is a little bit about the aeroplane general information, talking about airspeed and displays. I won't go too much into this. You have to remember that the NTSB, when they do these reports, assume no prior knowledge of the aircraft, so they go into a lot of what we would deem as basic information. But I will elaborate a little bit when we talk about Alpha Prot and Alpha Max and how they played an important part in the successful outcome of this incident. So we'll expand on that section a little bit. We'll talk a little bit about low speed energy or low energy warning and why it wasn't called, why it wasn't recorded on the cockpit voice recorder and on the flight data recorder. And then we'll move into the electrical and hydraulic system, and which will go on to explain a little bit as to what the IDG requires in terms of rotation to get electrical supply, and what the engine-driven pumps require in order to get hydraulic system, and how it was they ended up with all three hydraulic systems available to them. And then we're going to go into the engines, talk a little bit about the engines that were fitted to the aircraft and their times and hours on each engine, because I think that's quite interesting. I'm not going to go into the specifics of the makeup and construction of the CFM engine, so I don't think that's very important. As I say, the NTSB goes into a lot of detail here and assumes no prior knowledge, but for what we're trying to achieve here, we'll do a very quick review, but we're going to move on to what I think is the important part, which is the certification of engine testing, specifically when it comes to core and fan blade testing with bird ingestion, how that's completed, and the test conditions, just how far away the conditions that this aircraft experienced, and the size of the birds and the number that it ingested. So it had no hope really when you look at the testing conditions. So then we'll move on to airframe ditching and emergency landing and certification requirements, and we'll look at the ditching and the difference between the ditching checklist and the all engine inoperative or all engine fail ditching and forced landing. And we'll elaborate there on the decision to use flap 2 in landing, and the crew's decision to use flap 2 in this instance. Look at the ditching testing and certification and see just how close they got to those conditions despite the ditching requiring certification, assuming that both engines are running. A very small part on the weather at the time, and FAA guidance on airport wildlife hazard management, very small bit on that. And then we're going to finish off with air traffic control, what they saw, and a little information there about clutter on the radar, because there was a question asked in the report as to whether or not the geese, given the sheer number and size of these things, might have been seen on the radar to advise the pilots, or given them some advanced warning of the migrating geese, and why they didn't have that information. So we're going to elaborate a little bit more on that. So let's take a look at aeroplane information first. Okay, according to the weight and balance manifest provided by US Airways, the airplane departed LaGuardia with a takeoff weight of 151,510 pounds, which was below the maximum takeoff weight of 151,600, so only 100 kilos or so shy of the maximum takeoff weight. So assuming the fuel burn of 1,500 pounds during the climb to 3,000 feet and descent at idle thrust, of course, the airplane's weight when it ditched on the Hudson River was estimated to be 150,000 pounds, which interestingly, when we look a little bit later on, was about 4,500 pounds heavier than the ditching certification tests or assumptions. And of course, an important thing to note, it would have been above max landing weight as well. So moving on then to the airspeed displays, it talks about the definitions of green dots, F-speed, etc. But the important things that I want to just take remind ourselves of, which then moves into the flight envelope protections and why they play an important role, is alpha prot and alpha max. So let me just read these two to you just as a bit of a reminder of these protections. So the alpha prot, which is the alpha protection speed at alpha prot, is alpha prot is represented by the top of the black and amber strip along the airspeed scale. We know that the alpha protection speed corresponds to an alpha angle of attack at which the alpha protection mode becomes active, and it varies according to airplane weight and configuration. Also load factor as well. So maybe that's what they mean by weight. But alpha max, which is the maximum alpha angle of attack speed, alpha max is represented by the top of the red strip along the speed scale. Maximum angle of attack speed corresponds to the maximum angle of attack that may be reached in pitch normal law and varied according to aeroplane weight and configuration. So I've got a little picture here which I'll bring up just to show you, remind you of those characteristic speeds. But moving on, regarding the angle of attack protection, the Airbus Flight Crew Operations Manual, our FCOM, stated in part that under normal law, when the angle of attack becomes greater than a threshold value, the system switches over elevator control from flight mode to protection mode, in which angle of attack is proportional to the side stick deflection. So you remember, when you're in alpha protection, it's no longer a G requirement, it's angle of attack requirement. The angle of attack will not exceed the allowable maximum even if the pilot pulls on full aft stick. If the pilot releases the side stick, the angle of attack returns to the alpha protection threshold value and stays there. Under certain conditions, additional features built into the system can attenuate pilot side stick inputs, preventing the airplane from reaching the maximum angle of attack. So it's this here really that helped the crew, and the fact that they recovered the aircraft into normal law with full hydraulics and electrical supply gave them that angle of attack protection and prevented a stall with very minimal power. So let's take a look at that in a bit more detail. It talks about the low speed or energy warning. The oral low energy speed warning, repeated every 5 seconds, warns the pilot of the aircraft's energy level is going below the threshold under which he will have to increase thrust in order to regain a positive flight path angle through pitch control. However, low energy warning is overridden when the aircraft is below 100 feet radio altitude or when a GPWS alert is triggered. According to the CVR and FDR, GPWS alerts were triggered repeatedly during the descent, and no low energy level alert was generated because it's inhibited. GPWS takes precedence over the low speed, so that's why we didn't hear that. I think we raised it earlier on in episode 1 as to why perhaps they hadn't heard that, because it's inhibited with GPWS taking priority. So I want to move on now to the electrical and hydraulic systems, and it will go some way to explain, and I'll move on to a little bit later on in the report where it talks about the analysis, just to confirm which hydraulic systems and why they had the hydraulic systems available to them, why the aircraft maintained normal law. There's some interesting take-homes here. So the airplane was equipped with 2 integrated drive generators, the IDG, one mounted on each engine, which normally supply electrical power to the airplane systems. An IDG will only supply electrical power when the N2 speed is about 54% or more. The airplane was also equipped with an APU that drives a third or auxiliary generator, which can replace the electrical power normally supplied by the IDG. Well, obviously, when the engines had the bird ingestion, the twos were below 54% in both cases, which is why the RAT then extended to provide emergency electrical power to both the DC and AC essential, and the captain then elected to turn on the APU, which then restored normal power. So the important thing here is that you need N2 of around 54% in order for the IDGs to have sufficient energy to power the generators. If both the primary and auxiliary power sources are lost, a ram air turbine, the RAT, contained in a compartment in the left airplane belly fairing, supplies hydraulic power to the controlled speed motor generator, blue pump basically, which then provides electrical power to the airplane. During normal conditions, the RAT is retracted into the fuselage and does not operate. When all of the airplane's electrical power is lost and the airplane has an airspeed greater than 100 knots, the RAT will automatically deploy and begin providing electrical power. The RAT was found in the extended position when the airplane was recovered from the water. Both RAT blades were present and no major deformation of the blades was observed. So, as it's meant to do, it did its job. There was no power to the AC buses, so the RAT then extended. At that point, the aircraft would have been on battery power, giving limited displays. And of course, once the RAT then extended, it then gave the emergency power to the DC and the AC buses, AC essential bus. The airplane is equipped with three main, so that's the important take home there in terms of the IDGs. Now we'll look at the hydraulics. The airplane is equipped with three main hydraulic systems referred to as green, blue and yellow, which together supply hydraulic power at 3000 psi to the airplane's main hydraulic users, including the flight controls. The slats are powered by both green and blue hydraulic systems, and the flaps are powered by both green and yellow hydraulic systems. We covered all this in hydraulics some while ago. The three hydraulic systems are not hydraulically connected. They can be powered by the PTU, but there's no fluid connection. That's the important thing to remember. Each of these three hydraulic systems is pressurized by either an engine-driven or electric motor-driven pump. The blue, obviously, the electric, green and yellow by the EDPs, engine-driven pumps. The blue system's electric pump supplies hydraulic power when either engine is operating, that's off the AC buses, and the green and yellow systems engine-driven pumps are connected to the left and right engine respectively, and these pumps supply hydraulic power when their respective engine is operating. The engine-driven hydraulic pumps are driven by N2 spool and are able to supply a hydraulic pressure as long as the engine is rotating. So as soon as you have engine rotation, you'll have an element of hydraulic power, as it's an engine-driven pump. As long as the engine is turning, it's pumping, it's providing some power. Generally, the lower the N2, the lower the hydraulic flow can be delivered by the engine hydraulic pumps. So during this event, the engine-driven pumps provided sufficient power for the green and yellow. The blue pump was powered by the AC bus and also the RAT initially, and so the aircraft maintained full electrical power and full hydraulic services as well, because there was enough rotation. It's not like the IDGs where it requires a minimum of 54%. As long as the engines are turning in some capacity, there'll be some hydraulic power. And next time you're in the sim and you shut the engines off, just pop over to the hydraulic page and you'll see there that the hydraulic power continues to run for some time. Now I'm just going to move over to page 90 here quickly, which expands a little bit on the decision to use flap 2 for ditching. Okay, so the decision to use flap 2 for ditching. Airbus and US Airways engine dual failure checklists indicated that only blue hydraulic power would be available, and therefore that only slats would extend when configuring for landing. Although the dual engine failure certification assessed this worst case scenario, the possibility of having green and yellow hydraulic systems available was also considered. The FDR data indicated that during the accident event, all three, that's green, blue and yellow hydraulic systems were available, and that the flight crew was able to extend the flaps and the slats. In the accident scenario, NTSB notes that the selection of flaps 3 would have allowed the airplane to fly at a lower speed. Now at 15:29:45, the airplane was at an altitude of just 270 feet. The captain instructed the first officer to set the flaps. The first officer then stated that they were at flaps 2 and asked the captain if he wanted more. The captain replied, "No, let's stay at 2. About 1 minute later, the airplane was ditched into the Hudson River. During the post-accident interviews, the captain stated that he used flap 2 because there were operational advantages to using flap 2. He stated that using flap 3 would not have lowered the stall speed significantly and would have increased the drag. He stated that he was concerned about having enough energy to successfully flare the airplane and reduce the descent rate sufficiently. He stated that from his experience, using flap 2 provides a slightly higher nose attitude, and he felt that in the accident situation, flap 2 was the optimum setting. The NTSB concludes that the captain's decision to use flap 2 for the ditching based on his experience and perception of the situation was reasonable and consistent with the limited civilian industry and military guidance that was available regarding forced landings of large aircraft, critically without power. So talking about the engines then, they're fitted with 2 CFM International CFM 56 dual rotor turbofan engines. CFM being a partnership between General Electric in the States and SNECMA, I think you pronounce it, in France. Not that it's overly relevant to this incident, but a take home for us, I think, is that the engines that are fitted to the aircraft weren't of the same hours and flight cycles. The left engine at 19,182 and the right engine at 26,468 hours. So yeah, it just goes to show that whenever you're flying your aircraft, don't assume that both engines are of the same age and cycles. They get changed around from time to time, which is why it's really important that when we depart, we let the engine stabilise at 50% to make sure they both accelerate at the same rate. Or certainly one of the reasons why we do that. The engines may not be of the same age. It then goes into talking about the structure of the CFM engine. I'm not going to go too much into that in this episode, but something that's worth noting here is a brief description here about what may happen if the bird goes into the core and what may happen and what might be damaged if it goes via the bypass. So let me read into that before we actually go into the certification. So a bird may strike any part of the engine inlet area. If a bird enters the inlet area near the outer radius, it will most likely strike only the fan blades, continuing along the bypass duct and be ejected out of the rear of the engine. In this case, the fan blades may exhibit some of the leading edge impact damage, may bend and fracture. Debris continuing downstream can damage the bypass duct and fan outlet guide vanes. All of this damage negatively affects thrust production. However, typically the engine will still be able to operate at low thrust level. So via the bypass, the engine will obviously be impacted but still able to operate. However, if a bird enters the inlet near the inner radius close to the spinner, a portion of the bird may be ingested by the engine core, possibly damaging the internal components, including the inlet guide vanes, low pressure compressor and high pressure compressor vanes and blades, or the combustor. If the damage is sufficient, the engine may stall or flame out, rendering it unable to produce appreciable thrust. So during the inner radius near the spinner, an ingestion there can have much more critical damage. So next we're going to review the certification of the engine at the time. Now this engine was certified in 1996, so had to comply with foreign object ingestion certification at that time. And at that time it comprised of an ingestion of a large sized bird and medium sized birds, but critically what we're going to learn from here is where they're ingested. So the ingestion of a 4 pound, which is a large sized bird, may not cause the engine to 1, catch fire, 2, burst, which means release hazardous fragments through the engine case. It needs to be contained. 3, generate loads greater than those specified in section blah, 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 or lose the capability of being shut down. So that's the requirement of the ingestion of a 4 pound, which is a large size bird. Now, bear in mind that this incident aircraft took in at least 2 8-pound Canadian geese into each engine and at least 1 into the core of each engine. So when we talk about the size certification here, it was obviously way beyond what it was certified for. And then the ingestion of a 3-ounce bird, that's 1.5 pound, which is the medium size, may not cause more than a sustained 25% power loss, require the engine to be shut down within 5 minutes at the time of ingestion, or result in a potentially hazardous condition. So, according to the specifications at the time, the medium bird ingestion criteria for that size engine was 7 1.5 pound birds to be volleyed into the critical areas of the engine. 2 birds were mid-span, outer panel, and 2 birds were volleyed into the engine core area, and 5 birds were volleyed into the fan blade area at mid and outer and 2 intermediate locations. So for the medium size, 7 1.5 pound birds, 2 in the core and 5 at the outer and mid span. They're fired in quick succession in a rapid sequence to simulate a flock encounter. The large bird ingestion criteria for that engine was a single 4 pound bird volleyed into the critical area, but not into the core area of the engine. So under testing at that time, it was medium and large. Only the medium birds, and 2 of them went into the core for testing, but the large bird, which is a 4 pound, is not into the engine core. And bearing in mind, these engines took at least 1 8-pound bird into the core. Okay, the engine certification went through various testing, and the engine went through various modifications, obviously, before it was certified, and it talks through the various modifications that the engine went through. I don't think that's very important here, but another important thing about the testing was that these tests were also performed with an engine at 100% takeoff power, and we know that we're never at 100%, but the reason they do the tests at 100%, we'll talk about in a moment, but that's all to do with kinetic energy and stress for the engine. But of course, at 100%, you've got centrifugal forces going on here, which will send the bird to the outside, and also less of organic matter would end up going into the core because of the RPM. So we'll talk about that in a little bit more detail later on. More recently, the FAA adopted new regulations under a different amendment, which became effective in November 16th, 2007, which introduced a new class of bird, the large flocking bird, for testing fan blades, flammable fluid lines and support structure. The large flocking bird weight requirement contained in that section was 4.5 or 5 half-pound birds, depending on the engine size, and the engine had to continue running at a decreasing sliding scale from 90% maximum takeoff power, interesting, for 20 minutes after ingestion. These changes harmonise the FAA and EASA bird ingestion standards for aircraft turbine engines certified by the United States and EASA countries. Only newly designed engines obtaining a TC must meet these latest requirements. Therefore, the accident engine was not required to meet any of the new requirements that resulted from the rule change made after this TC was issued. So just to finish this off now, I'm going to go over to the NTSB findings on page 83, which expands a little bit more on the bird testing, and not the bird testing, but the incident engines and what they ingested. So it's very clear here. We know that the size of the birds that the engines were exposed to, that it went way beyond certification, and we could see the damage it caused to the engine. So there's no way they're going to test the birds into those engines of that size, because it obviously leads to destruction. So it talks more about that here, and the balance of probability versus testing. Each engine ingested one 8-pound bird into its core, preventing the engines from providing sufficient thrust to sustain flight. Just a reminder here, the engines took at least 2 birds, 8-pound Canadian geese in total, from what they found from organic matter in the findings, but it took at least 1 into the core, indicating that an engine of this size cannot withstand the ingestion of such a bird into the core and continue to operate. Further informal discussions with industry and the FAA revealed that it would not be practical to build an engine that could withstand ingesting a bird of this size into the core because of the performance and weight penalties of such a design would entail. These discussions also revealed that ingesting one 2.5-pound bird into the engine core, which is the current engine core ingestion test requirement, is already considered a stringent test of the engine core. So there you go. The NTSB concludes that the size and number of birds ingested by the accident engine well exceeds the current bird ingestion certification standards. Well, that's obvious. The accident event highlighted other considerations that could be addressed during tests related to small, medium and large flocking bird. These considerations are discussed below. One of them, I believe, is to do with the RPM, but we'll talk about that in a second. The test requirement contained in the certification for ingestion of small and medium flocking birds require that for an engine of this size, one 2.5-pound bird will be volleyed into the core, and 4 1.5-pound birds be volleyed at other locations of the fan disc. Each accident engine ingested one 8-pound Canadian goose through its core, much more than the weight used in current tests. Therefore, the accident engine sustained a significantly greater impact force than that which would be certified. The FDR indicated that the fan speed of both engines just before the bird ingestion was only about 80%, which is consistent for an airplane and atmospheric conditions at that point in flight, and is well below the bird ingestion test fan speed requirement of 100%. The small and medium flocking bird certification test requires that 100% fan speed be used. This condition involves the highest kinetic energy of the bird relative to the fan blade, which is likely the most critical condition for damage to the fan blade itself. However, an additional consideration for the severity of core ingestion event is the volume or bird mass. Excuse me a moment. Therefore, the lowest operational fan speed should be used during the tests related to small and medium flocking birds, so that a larger portion of the bird mass passes through the fan blades. Additionally, a slower fan speed will cause less centrifuging of the bird mass as it passes through the fan, which would allow a larger portion of the bird mass to pass through to the IGVs and the core components, causing higher impact forces on them, reducing the fan speed during the certification tests to that expected during takeoff conditions would allow more bird mass to enter the engine core. So if we're going to use smaller, lighter birds, then at least reduce the fan speed so more of it is ingested. That's, I guess, what they're trying to conclude. The NTSB concludes that the current small and medium flocking bird test required by that certification would provide a more stringent test of the turbofan core resistance to bird ingestion if the lower expected fan speed for the minimum climb rate were used instead of 100%. And this is what again goes on to make various recommendations. Interesting, the current section, large flocking bird cert tests require the ingestion of one large flocking bird. However, during this test, the bird is not directed into the core. Therefore, only the fan blades, flammable fluid lines and support structure are tested. Further, the test is limited to engines with inlet areas of greater than 3875 square inches, and smaller transport aeroplane engines such as our engine with an inlet area of just 3077 are exempt from this test. The evidence from this accident shows that large flocking birds can be ingested into smaller transport category airplanes engines and pose a threat to engine core as well as fan blades. However, the large flocking bird tests are not required as part of certification process for this size engine. So very interesting. Okay, so let's move on then to airframe ditching and emergency landing certification requirements. And a really interesting thing, of course, with this, with regards to ditching, it assumes that the engines are still running. So when I show you later on about the criteria in terms of pitch and airspeed and glide slope and descent rate, etc., just how close they came to those ditching certification without engines running was due, of course, to the wonderful systems and protections afforded by the Airbus. And of course, when you look at the ditching checklist and you compare that, as it assumes both engines are running and using as much flap as possible, to the all engine failure, both at cruise and at low level, there are differences there that are worth reviewing. So without further ado then, let me just go into the report. So certification for ditching is optional since not all aeroplane types are used to conduct extended overwater operations, EOW. The Excellent airplane was certified for ditching. The Airbus airplanes are designed and certified according to the requirements of 14 CFR Part 25, Airworthiness Standards, Transport Category Aeroplanes. Ditching contains a transport category certification requirements that pertain to the behaviour and response of the airplane ditching. Therefore, if certification with ditching provisions is requested, the airplane must meet the requirements of that section. Okay, sounds like a lot of gobbledygook, that, doesn't it, really? Each practicable design measure compatible with the general characteristics of the airplane must be taken to minimise the probability that in an emergency landing on water, the behaviour of the airplane would cause immediate injury to the occupants or would make it impossible for them to escape. So this is all part of the design requirements. The probable behaviour of the airplane in water landing must be investigated by model tests or by comparison with airplanes of similar configuration for which the ditching characteristics are already known, and that's what happened in this case. They use a different type of airframe. It must be shown that under reasonable probable water conditions, the flotation time and trim of the airplane will allow the occupants to leave the airplane and enter in life rafts required by certain section. If compliance with this provision is shown by buoyancy and trim computations, appropriate allowance must be made for probable structural damage and leakage. So of course, if the aircraft is buoyant, then there has to be an allowance for damage as part of that testing. In addition, at the time the accident airplane was certified in accordance with those criteria, emergency landing conditions. The airplane, although it may be damaged in emergency landing conditions on land or water, must be designed as prescribed in this paragraph to protect each occupant under those conditions. Some of these conditions are an upward G of 2.0, forward G of 9, that's quite significant, sideways of 1.5 and downward of 4.5. As noted, the FAA approved the A320 Model TC on December the 15th, 1988. The ditching certification for the airplane was based on over 200 ditching tests conducted on scale models of A300B2 and Dassault Mercury aeroplanes, taking into account their similar geometry to the A320. Quite interesting. So in accordance with now the Aeronautics and Space Administration, NASA, reports from the 1950s, the tests were conducted to identify the approach scenario in terms of airplane parameters, glide slope, pitch, and airspeed. So on January the 21st, 1988, the Airbus certification test reported that the fuselage of an A320 would undergo no destruction liable to create a water passage if the airplane ditched with the following parameters: the landing gear retracted, 11 degrees of pitch, which you'll notice is in the ditching checklist, 0.5 degree glide slope, and flaps in the landing configuration for minimum speed. Of course, remember that assumes engines running, and it also assumes, worst case, that you've just got the blue hydraulics, which we'll come on to a little bit later on. According to Airbus, the ditching certification criteria also assume that engine power is available. and the descent rate of 3.5 feet per second, which is 210 feet per minute. So let's have a look at the table. I'll bring it up here for you, and this goes on to show the certification and the accident flight, and it's quite amazing here actually. The mass in pounds 145 versus 151, so the aircraft was obviously over certification weights. Pitch attitude 11, they achieved 9.5, which I don't think is too bad under the circumstances. Airspeed 118 versus 125, again pretty close. Glide slope, it says -1 here, but it mentioned earlier on about -0.5, but they achieved 3.5 glide slope. Not bad, almost a 3-degree glide with no engines. And a descent rate of 210 feet per minute, in this case 750, and it talks about external pressure, etc., which I'm not sure is overly relevant. So there we have it, the ditching tests, and you see there in the table that they actually achieved something very close to it. So we'll move on now to the Met conditions. Not going to talk a huge amount about this, but suffice to say that the Central Park surface weather observation indicated winds at 290.8 knots, 10 miles visibility, they measure it in miles, with a cloud ceiling of 3,700 feet broken. Temperature was -6. But interesting, the National Oceanic and Atmospheric Administration, National Ocean Service, owns and maintains a buoy at a station in Battery, New York. And according to that, the temperature of the Hudson River near the accident location time was 5.2 degrees C. Whew, that would have been rather chilly. So you can see why those that decided to that bailed it, decided to return to the aircraft fairly promptly, because I mean that's got to be cold water shock. I would imagine. Okay, so the last thing I'm going to talk about now is the radar, and talk a little bit about clutter, and about what the air traffic controllers can see, because there was some talk about the sheer size of this flock. Why wasn't it picked up by the radar? And I think, if memory serves me correct, we talk a little bit about the fact that they periodically or momentarily lost the target of the aircraft, or the identification of the aircraft as it was handed over to area control. But anyway, let's just talk about it very quickly. So air traffic control, LaGuardia ATC provides air traffic services from surface to 2,000 feet. The New York TRACON provides air traffic services from 2,000 to 15,000 feet within 5 miles of LaGuardia. New York TRACON was responsible for flights descending into and climbing out of LaGuardia, John F. Kennedy, New York, Newark Liberty International Airport, Newark, New Jersey. So a number of very busy airports there at the time. For at least 1 hour before the accident, ATC provided no pilot reports of bird activity. Further on the day and before the accident, no bird warning advisories were broadcast on the Automated Terminal Information Service, which is a continuous broadcast of recorded non-control information in selected terminal areas. Interestingly though, the FAA Airport Facility Directory entry for LaGuardia included the following advisory: flock of birds on and in the vicinity of the airport. So I'm not sure why that didn't get into the ATIS, but the Airport Facility Directory for LaGuardia included that advisory. So whether the pilots actually had access to that at the time, I don't know. ATC radar coverage for LaGuardia area is provided by Airport Surveillance Radar, ASR, located at JFK. The ASR is a short-range 60-mile radar that provides position track information to controllers at the New York TRACON and other control towers, including LaGuardia ATC, for aircraft operating within terminal airspace. So they all share that radar. ATC services provided by LaGuardia tower controllers during taxiing departure from runway 4 were reported to be normal. At 15:25:51, the captain initiated contact with New York Tracor on LaGuardia controller, and at 15:27:01, the airplane's altitude was about 2,500 feet, recorded by radar data at EWR and JFK radar sites, indicated that the airplane's path intersected a string of unidentified primary targets. A subsequent review of the radar replay showed that these primary targets were not displayed to the LaGuardia departure controller. So let's take a look at how this might have happened and why didn't the controller see them on his radar screen. So let's have a look at the airport surveillance radar, which is over on page 29, and talk about what the controllers can see in terms of correlated and uncorrelated targets and why they may choose to remove it as they perceive that to be as clutter. Remember, it's busy airspace. So although ASR9 radar system is primarily intended to track aircraft by identifying an onboard transponder, we'll all know that as SSR, secondary radar, it has a limited ability to provide information about other phenomena such as birds, balloons and precipitation by detecting the radar energy reflected from these objects. Radar returns based on reflected energy rather than transponder signals are known as primary radar or primary returns. Many primary returns are not of interest for ATC purposes and could potentially distract controllers or interfere with the system's detection of phenomena of interest. Therefore, primary radar returns are filtered from the system except for those that appear to be relevant for ATC purposes. It'd be really interesting actually if there's anybody that has air traffic control experience or area control that can add some context to this. It'd be really useful. In particular, the radar system attempts to identify and retain targets that move consistently, remain visible from sweep to sweep, and have a ground speed of at least 30 knots. If a primary return meets this criteria, it is likely to be classified as correlated target, indicating a high level of confidence that is of interest for ATC purposes. So it has to meet those criteria for it to be deemed as correlated. If a primary return does not meet this criteria, it may be either discarded as clutter, for example returns produced by non-moving objects such as terrain or bridges, or if the return cannot be conclusively discarded as clutter, classified as uncorrelated targets and then forwarded to the display system. Controllers can then opt to display only correlated primary targets or to display both correlated and uncorrelated primary targets. So that's the choice of the controller there if it doesn't fulfill the criteria of clutter. A review of the recorded radar at the time surrounding the bird strike at about 15:15 to about 15:35 indicated that 14,614 primary targets were detected, 1,716 of which were correlated and identified as having flight characteristics similar to an aircraft. However, according to the recorded keyboard entries and filter selections in the affected LaGuardia departure controller position at the time, the controller had chosen to display only correlated primary targets, which did not include the primary returns associated with the flock of bird. A post-accident replay of LaGuardia departure control display shows no primary targets until the collision occurred. So very interesting. Okay, so just to finish off then, talk about ATC guidance. There's quite a large piece here which talks about data blocks for air traffic control and the temporary loss of position information. I didn't find that overly relevant to what we're looking at here, but you can obviously read that. It starts on page 27, 110.3, 1 ATC guidance. So I've skipped it here, and I'm going to take a look at the TCAS, which we mentioned earlier on, of this helicopter that had a bird's eye view of everything that's going on. And I've skipped it because because the TCAS event occurred, it highlighted the position of Cactus 1549. So even though they lost the data block initially, it was then highlighted because of the TCAS event when it was concerning this helicopter. So let me read into that for you. About the time that the captain stated the airplane would be going into the Hudson River, two AS-350 helicopters, they were November 152 Tango Alpha and November 461 Sierra Alpha, were conducting air tour operations nearby over the river. The LaGuardia Air Traffic Control Class B airspace CBA controller, who was responsible for monitoring the CBA surrounding LaGuardia, stated that he immediately started looking for Flight 1549 after he learnt that it was returning to LaGuardia. He stated they did not see it on the radar display, so he began manually selecting each unidentified target on the display to bring up the flight data for the associated aircraft. While the controller was trying to find the airplane's location on the display, the airplane passed close to November 461 Sierra Alpha, which resulted in a conflict alert between the accident aeroplane and the helicopter at 15:29:10. The conflict alert caused the ARTS to force the flight data block information for the airplane onto the tower controller's radar display, making them aware of the airplane's position and altitude. 9 seconds later, the CBA controller advised November 152 Tango Alpha of traffic shortly after the helicopter pilot reported that he had the aeroplane in sight and that he was maintaining a visual. So despite the fact that they lost the data block, it was then came up on the radar display when there is a TCAS. So one would assume if you experience a TCAS event, then your data block will be visible to the air traffic controller. So I thought that was a little piece of useful information there. Okay, so I'm going to conclude with that because then we go on to structural damage for the aircraft, and then we take a look at survival aspects of some really interesting stuff in there. I'll talk more about that in the next episode. We also look at CRM and threat area management training. So lots to be taken from that as well. So lots more to come. Thanks very much for tuning in. I hope you found it interesting. And remember, keep the plates spinning. And I'll look forward to seeing you again very soon. And bye-bye for now.